The next speaker is Kasia Tokarska. Kasia gained her PhD at the University of Victoria in Canada in 2017. She then spent 2 years as a researcher in Edinburgh before moving to ETH Zurich in 2019. Her work is focused on the links between carbon emissions and global climate change, especially in determining the remaining carbon budget we have before given temperature level might be reached. For example, those set out in the Paris Agreement goals. Kasia will address robust future climate projections using observational records to constrain the projected future changes. Kasia, please.
Thank you very much for this invitation. It's a pleasure to be speaking to all of you. And I think this talk is going to focus on how we can use the observational records from various variables, including temperature, to constrain future climate projections in climate models. And this is the work I've been doing at ETH Zurich in collaboration with several colleagues. So before we go on to the key part of the talk, I just wanted to briefly introduce the two core quantities, which is the transient climate response, and it's a measure of the strength and rapidity of climate change in response to CO2 forcing, and then also the equilibrium climate sensitivity, which is the eventual response in response to the CO2 forcing. And the new IPCC report that came out last year, the AR6 physical climate basis report, updated those ranges to a little bit narrower ones that those reported previously. What is very interesting is that the ECS range is said to be likely between 1.5 and 4 degrees Celsius. However, if you look at the recent generation of the new climate models, from the CIMIC 6 generation, they actually have much higher climate sensitivities. So one thing to keep in mind that moving from the transient, so like the present day conditions, to future long-term conditions, we actually have a lot of nonlinear feedbacks and processes that we need to take into account. And here, looking at the selection of CIMIC 6 models, we can see that about 1/3 of them have equilibrium climate sensitivity values over 4.5 degrees Celsius, which is outside of this likely range of equilibrium climate sensitivity as constrained by the IPCC. So the first question arises, why those models show such high climate sensitivity values? And this is nicely answered in this paper, where the main answer can be attributed to stronger positive feedbacks and reduction in shortwave low cloud amount and lower albedo in the exotropics. So it's kind of like related to the different strengths of feedbacks. But what I'm mostly interested in is how can we use those model responses given that they warm more than previously expected? And can we actually use them for future projections? If we do want to use them, then also how can we constrain those upper ends of those responses? So there are, coming back to the IPCC report, the most recent one, you can see here a spread of CIMIC 5 models and the CIMIC 6 models. So the high ECS models will be up here. And as you can see, the constrained IPCC range of climate sensitivity shows that these models are less likely, that are on the upper end here. And likewise, if we look now into the projections of the end of century warming in CIMIC 5 models, they are much smaller range compared to the CIMIC 6. And if you apply observational constraints on the CIMIC 6 models, you also end up with this kind of constraint estimate, which is similar to CIMIC 5 and kind of also shows that this higher warming models will be less likely. So I want to present you 3 different methods of how we can use observational constraints to help us provide more robust projections of future climate, and also how to kind of, in a sense, get the most likely response, which is not necessarily the highest warming response. So the first method would be using the emergent constraint. And here we rely on some observed quantities, such as the temperature trend over the recent decades that can be observed. And then we constrain the future projection of, for example, TCR or future warming. And this method relies on stronger statistical relationships between those two variables. And also we need some sort of out of sample testing, because if we find a constraint, we want to make sure it's robust and it doesn't arise due to spurious correlation. And if the constraint indeed is robust, it can reduce uncertainty in future projections. So here is an example why we could use this most recent observed warming trend from the post-1980s. And the main reason for it is that the aerosol forcing trend is approximately 0. The aerosols are still present, but the trend is much smaller compared to the greenhouse gas trend. And that's why kind of different fingerprinting approaches or detection attribution also become easier in this post-1980s period. And here's an example how we can apply this constraint. So using the observed temperature trend, you can see that there's a strong correlation between this and the future warming end of century. And you can provide the constraint response, which would be the kind of this blue rectangle here. And the constraint response is narrower and smaller than the upper range of some of those models here. And this method has been applied, for example, in this recent paper by Claudia Tebaldi and colleagues, who provided a constraint range using observational constraints both on CMIC6 and CMIC5 models. And as you can see, for CMIC5, it doesn't make much difference. The range is very similar because the CMIC5 models were not warming as much. But for the CMIC6 models, the high warming models are outside of this observationally constrained range. And comparing end of century warming in either SSPs or RCP scenarios, you end up with actually similar range once those models are observationally constrained. And what are the implications, for example, for the Paris Agreement target? So similarly, this is for the high warming scenario and for the ambitious mitigation scenario. You can see that like the upper end of those projections of warming is brought down by application of the observational constraint. And as a result, the Paris Agreement, for example, target is more likely to be met, especially in this ambitious mitigation scenario, while it was exceeded in the kind of unconstrained range. So the second method to constrain models using observational records in order to provide more robust projections of climate change is using the model performance and weighting approach. And here you want to firstly consider like are models actually consistent with the observations of the recent period, but also other responses independent of each other. And you also don't want to select too many models from the same model family because then you'll be biased towards one particular modeling center. And using this approach, different papers also arrived to similar conclusions consistent with the previous studies. So here, and similarly, the gray rectangle would be the model response unconstrained, and the colored rectangles are the ones with observational constraint. And you can see very similar conclusions that the upper bound is actually brought down. So applying the observational constraint makes the future projections more robust, and the upper end of the end of century warming is less likely once this observational constraint is being applied. And then there's also a Bayesian approach. So you can here actually use the entire historical record of observations and also apply it to the climate models. And as a result, you end up with this narrower, darker constraint range compared to this not constrained range in the lighter color. So especially for the high warming scenario, historical plus SSP 585, you can see that the very top end of the CMIC6 models here is quite unlikely, and the observational constraint upper end is much lower. So there are three quite different methods, but all of them lead to the same conclusion that using the CMIC6 models as they are might lead to overestimating of the warming in the future. And if you apply observational constraint and either you select models that are consistent with observations or you correct the models to match the observations for the present day and apply this correction as you go on, you end up with more robust future projections. And those different ways of constraining the global mean warming have been used in the recent IPCC report. And that's basically, here's the unconstrained CMIC6 models and constrained using the three different methods I showed here. And then also they use the synthesis approach using climate model emulators. So all results lead to similar conclusions that the constrained warming range is narrower and not as high on the upper end as the unconstrained range of CMIC6 models. And so how can we solve this hot model problem? So I think for global mean temperature, the approaches I suggested are quite straightforward to apply. However, the problem arises like if we have variables other than warming. So for example, if we have precipitation, the data sets might be harder to apply, especially on the regional scale, and the internal variability becomes higher. So there are also ways of dealing with those hot warming models to produce future projections that are kind of consistent with the observational record. So firstly, the emergent approach that I showed earlier also works on the regional scale as well. So you can use a multi-model fingerprint of spatial variation. Even if you remove the global mean signal, you still can use the spatial pattern to use the emergent constraint and constrain the future response. Another approach, which is widely used by the new IPCC report, is this per degree of warming approach, which relies on basically looking at the time slices at 1.5, 2 degrees, 3 degrees of warming and comparing the model responses across those time slices specific for the warming level, as opposed to comparing the models in time. So you just basically compare a map of warming or a map of precipitation at a given level of warming. And here's an example of warming spatial pattern at different levels of warming. And here you can see that basically this climate change amplifies as the global warming increases. And also it's largely scenario independent. So even though we would expect like aerosols to have regional effects, once you average across all the models and across all the scenarios, like the pattern becomes quite evident. And it also works for precipitation. So similarly for precipitation, you have 1.5, 2 degrees, 4 degrees of warming. So the climate change usually amplifies in the same kind of regions as it becomes evident. And then a similar approach they also apply to total column soil moisture, and likewise it kind of just becomes stronger as the warming continues. So there are of course some drawbacks of this per degree of warming approach because it does not account for the pattern effect of like the various warming states, especially for different scenarios that include high non-CO2 forcing levels. But to a first degree of approximation, we can say that this approach is like largely scenario independent, and it is the recommended way of dealing with hot warming models, especially when looking at spatial response of different variables. And then there's also new approaches that are being suggested, which is like machine learning and introducing data-driven methods, where a lot of machine learning models, they want to learn from observational data products to either predict the future near-term responses, and they are quite good at predicting on like kind of sub-seasonal to seasonal forecasts. But if we think of like the long-term climate signal, especially doing in different scenarios, where machine learning can be useful is like kind of like using the hybrid models. So you still use the climate model that is physics driven, but then you learn from all the data available from the observations to try to constrain this kind of physics model in some different ways. And there are various approaches also suggested using multivariate constraints that use different variables at the same time to provide more robust projections of climate change, and kind of using this merge of physics-driven models, but also learning from the large availability of the data available. So just to briefly summarize, the new generation of CMIC6 models shows stronger positive feedbacks on average, and a lot of models have like reduction in shortwave low cloud amount and lower albedo in the exotropics, leading to their high ECS values. And as a result, the global mean temperature is likely biased high in some, especially in the multimodal mean, because some of those high warming models would bring the mean high. And therefore, we need to apply observational constraints so the future projections would be more likely because the raw responses are not. And one way to deal with that would be using the per degree of warming approach. So instead of averaging models in time, you average them per degree of warming. And this is kind of what the IPCC does and many other studies. So thanks so much for your attention, and I'm happy to answer any questions.
Thank you very much indeed, Kasia. Can I invite questions for Kasia, please? In the room we have Tim.
I've got a second question. Thank you very much for that. You mentioned for the observational constraints, it's useful to use the warming trend over the last few decades, essentially to favour models that simulate that warming trend the best. because the global average aerosol forcing is fairly flat over that period. But of course, although the global average is flat, there's been quite a large change in where the emissions of aerosol come from over that period, moving from North America and Europe across to South Asia and East Asia. Does that geographical change matter for the results, do you think?
Yeah, that's, I think, a really good point. And for the approaches that use global mean warming as the constraint, I don't think this would matter. But the second method, which was the model weighting, it's based on a grid point basis. So this would account for it because it's using the kind of spatial pattern of warming and then trying to weight the models that are closest to the observations higher. So I think it depends on the method, but yeah, I think it's quite interesting that while the aerosol patterns can affect the global temperature trends, for some reason in many of those methods, it doesn't have much effect, because even like using the different SSP scenarios, the very ambitious mitigation scenario, which has like very high aerosols, and then the SSP 585, you don't really see much kind of difference in applying those methods to those scenarios.
Kasia, I wonder how these constraining by observations might work when you look at ice caps and glaciers. Ben mentioned the rapid retreat of many glaciers. I was working on the Peyto Glacier in the Rockies in Banff National Park last summer, and the glacier snout retreated by 200 meters just in one summer. So this is a hot occurrence. Can you give some idea of how you might incorporate the observations in constraining projections on ice fields and glaciers?
This is surely outside, I guess, of my scope of my main research, but I think it definitely, especially like the data-driven methods and the machine learning methods would be quite helpful there, finding kind of like the near-term predictions. I believe that like even the CMIC 6 models, most of them, they don't necessarily include ice sheets. Maybe some of them include glaciers, like if they're at higher resolution, but certainly, I think like observations are like very important to tune either model emulators or various approaches to deal with the near-term predictions of it. And as you can see, like I have actually a glacier picture in the end, because when I was studying in Canada, that was like one of my favorite things to do was seeing the glaciers there, and it's so sad to see how quickly they melt.
Thank you. If there are no more urgent questions, I think it's time to firstly congratulate the seminar organizers from the Climatic Research Unit for putting together such a coherent program, observations and the way in which those observations might be used, with an adequate opportunity to highlight the importance of CRU's contribution over the last 50 years. So thank you very much for that. And I'd also like to thank our 4 excellent presenters. Phil, here in the room, Kate, and Ben and Kasia online. All excellent presentations with wonderful slides. I'd like to thank you on behalf of the whole audience.